Hi everyone, welcome to this week's lecture video. This week we're going to talk about regression. Here's the outline. We'll start with the easiest linear regression. Simply fit a line. Then we'll talk about linear regression with multivariable and polynomials. Finally, we'll discuss a problem called overfitting and a procedure to deal with overfitting called regularization. So we start with the simplest case, fit our data with a line. That's why it's called linear regression. Following the spirit of this course, let's consider a physics example, predicting the energy of a particle using information from a calorimeter. Calorimeters are a kind of detector which measure the energy of a particle. A particle comes into a calorimeter and interacts with materials in the calorimeter. This incoming particle then produces a bunch of other particles along its trajectory inside the calorimeter. This bunch of particles is called a shower. The plot below is a simulation of electromagnetic shower produced by the incoming particle along the direction it travels through the calorimeter. The bunch of colorful lines which look like fireworks is the shower produced by the incoming particle. We expect the energy of the particle depends on the properties of the shower it creates. For example, number of particles in the shower. So if I plot the energy versus the number of shower particles with our training data, represented by the red dots here, it probably looks like the plot on this slide. And our goal is, given the number of shower particles of a new data point, represented by the blue cross on the x-axis, predict where this new data point should lie on this plot, that is, predict the energy of this new particle. Well, it looks like the energy of the particles is proportional to the number of shower particles. Let's fit the data with a line. What does this line do? It allows us to make a prediction of the target, the value of y, if we are given the value of x, which is called a feature of the data. The line represents a hypothesis or model of the relation between x and y, which is given by the simple formula y, or h of x, equals theta 0 plus theta 1 times x. Theta 0 and theta 1 are the parameters of the hypothesis h of x, which, as you know, represent the intercept of the line on the y-axis and the slope of the line. How do we find the line? The line is the one that gives the closest predictions to all the points from the training sample. Here, the vertical blue lines are the differences of the predicted y values and the true y values of each data point. Mathematically, we fit the line by finding the parameters theta 0 and theta 1 that minimize the sum of squares of each blue line, the difference of y values from the line h of x, and the true y values yi from each point xi, yi of the training sample. That's sometimes called the method of least squares. The function sum of squares is called the objective function, or sometimes cost function or loss function for the regression. This is the function we need to optimize or minimize for the regression. However, most of the time, the target may depend on multiple features, and thus we want to do a linear regression with multivariables. For our physics case of energy regression, the energy of the particle may also depend on the depth of the shower, the length that the particle can penetrate through the calorimeter. So let's plot the energy versus the number of shower particles and the depth of the shower on a 3D figure. Here, I've tried very hard to make this plot look like 3D, but you have to imagine that the dashed z-axis goes into the screen, and the smaller dots are the ones that are further away from you, which have larger z values. Nevertheless, the same idea of linear regression can be extended to this multivariable case. Again, by minimizing the squares of lengths of the blue lines, which are the differences of the predicted y values and the true y values of each data point. The formula of the hypothesis is now y, or h of x and z, equals theta 0 plus theta 1 times x plus theta 2 times z. It has three parameters, theta 0, theta 1, and theta 2, and the resulting fit is actually a plane on this plot. What if we want to do a fit with a polynomial function, like fitting the red dots on the xy plot with a second-order polynomial? In fact, it's the same as fitting with multiple features. We can view the x squared as another new variable z, and it will be the same situation as in our 3D case. Therefore, linear regression can also be extended to fitting with polynomials. The number of parameters we choose can affect the performance of linear regression. For example, if we only fit with one parameter, the result looks like the left-hand side where we have a horizontal line on the plot. This means it predicts the same value of y for any given x value, which is definitely a bad prediction for our data. It is because there are too few parameters in the regression, and thus, the hypothesis cannot capture the dependence of the target y on the feature x. This situation is called underfitting. On the other hand, if we fit the 5 data points with a fourth-order polynomial, we may result in a wiggly curve of the plot on the right-hand side, which goes through every data point, and thus a perfect fit. But we don't believe in it because it is very unlikely that the target value y has such unnatural dependence on the feature x. This is the case of overfitting, meaning the regression tries too hard to fit all the data points because there are too many parameters. While it is relatively straightforward to fix underfitting by considering more features or parameters, the case of overfitting needs more attention. To see why overfitting is bad, remember it happens when there are too many parameters or features. Therefore, the learned hypothesis may fit the training set too well, such that the sum of squares is close to 0, but it fails to generalize to new samples. Here, I add a blue dot representing a new sample from the testing data, which is an independent data set from the training data. And you can see, while the curve fits all the red dots from the training data perfectly, it fails to make a good prediction for the blue dot. This is what we mean by overfitting hypothesis fails to generalize, and this is bad. So what should we do to avoid or fix overfitting? Usually there are two options. One, manually reduce the number of features or parameters, like using physics to remove features that we believe have little effects on the measurement of particle energy. Two, we employ a method called regularization, which adds a penalty for the sizes of parameters. To get an intuition of how regularization works, consider a toy example where we have only 2 data points from the training data, and it is represented by the two red dots on this plot. And we fit them with a line. Because 2 points determine a line, we obtain a line that passes through the two red dots, meaning it fits the 2 points perfectly, and the sum of squares is 0. This is a case of overfitting, because when we add the blue dots from testing data, the line from the 2-point fit cannot be generalized to the blue dots, and it offers bad predictions. So, we apply regularization. Instead of just minimizing the sum of squares, we add a term lambda times theta 1 squared to the objective function and minimize them altogether. Here, lambda is called a hyperparameter, and theta 1 is the slope of the line as before. If we do this, we probably end up with a line that has smaller theta 1, and it looks like the one on this plot, which certainly gives better prediction of the y values for the blue dots. To get an idea of why regularization works, we put the two lines on the same plot. The black one is from linear regression with the method of least squares. And the blue one is from regularized regression with the extra penalty term, lambda times theta 1 squared. Let's see if there's a change in the value of x, say a change delta x in the number of showered particles. What's the difference delta y for the predicted energy? Because regularization adds a penalty on the size of the slope, the blue line has a smaller slope than the black line. Therefore, for the same delta x, the change delta y from regularized regression is much smaller than delta y from the simple linear regression. This means the prediction y is less sensitive to x for regularized regression. Recall that without regularization, the hypothesis line just comes from the 2 points from the training data. So we can also say that with regularized regression, the prediction y is less sensitive to the training sample. And that's why it is more feasible to generalize the hypothesis from regularized regression. To extend regularization to multi-parameters, we add a penalty term lambda times the sum of squares for all parameters except for theta 0 to the objective function we wish to minimize. That is, we do not penalize the overall constant theta 0. And how do we determine the value of the hyperparameter lambda? We can try different values of lambda on a validation sample, which is statistically independent from the training sample, and determine the best choice of lambda. Then apply the learned hypothesis on another independent testing sample to evaluate the performance. Just to mention that there are different ways to do regularization. Two common algorithms are the ridge regression, where the penalty term is the one we've shown on previous slides, and lasso regression, where the penalty term is lambda times the sum of the absolute values of all parameters starting from theta 1. To summarize, linear regression is to fit a training sample with a line by minimizing the sum of squares. And this can be generalized to cases with multivariable, meaning more than one feature, or with polynomials. When there are too many features, one may overfit the training sample. The consequence is that we cannot generalize the result to test samples. A way to avoid overfitting is regularization, which adds a penalty for the size of the parameters to make the prediction less sensitive to the training sample. For example, ridge regression means to minimize sum of squares plus lambda times sum of theta I squares from I equals 1. The hyperparameter lambda can be tuned with validation samples. That's all. See you next week.